5-2 binomial probability distributions. A binomial probability distribution results from a procedure that meets these 4 requirements. The procedure has a fixed number of trials. The trial must be independent, meaning that the outcome of any individual trial does not affect the probability in the other trials. Each trial must have all outcomes classified into exactly 2 categories: success or failure. The probability of a success remains the same in all trials. This is a sack, and there's 5 balls, 1 red, 1 purple, 1 blue, 1 green, and 1 black. Now, if I want to know the probability of picking a red ball, we know there's only 1 red ball out of 5 balls. It's 1/5, which is equal to 0.20 or 20%. We have with replacement and without replacement. With replacement means after I pick that red ball, I put it back in. And I have the same exact probability for the next time. Maybe the next time I want to know what the probability of picking a blue ball. It's still 1/5. This is called with replacement because after I pick the ball, I put it back in. Now, if I wanted the probability of red, and when I picked a red, I didn't replace it, this is called without replacement. Now, every outcome is going to be different. First, I pick a red ball, and it's 20% or 0.2. But if I don't replace it, then I only have 4 balls in the bag. Now, the probability of a success remains the same in all trials. That wouldn't be true. Notation for binomial probability distribution: S, success, and F will denote as failure. And those are our 2 possibilities. N is the fixed number of trials. I'm going to do this 20 times. X is a specific number of successes in N trials. Let's say I'm going to play 5 games of tennis. X is the number of successes in N trials. I want to know the probability of winning 3 games. The probability of success, 60% or a 0.60 chance of winning. If I have a 0.6 or a 60% chance of winning, I have 1 minus 0.6 chance of failing or losing, which is 0.40. This is equal to P, and this is called Q. And then P of X is the probability of getting exactly X successes among the N trials, the probability of 3. I'm going to show you how to do this problem and get the correct answer on StatCrunch. When an adult is randomly selected with replacement, that's very important because remember, without replacement, the probability changes. That the person knows what Twitter is based on results from a Pew Research Center survey. Suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. We're going to go Stat, Calculators, Binomial. N is equal to 5. P is the probability of success. That's the probability that the person knows what Twitter is. This is 0.85. And now the probability that X equals 3, exactly 3 of 5. We hit compute. This number 0.13817 and so on. That is our probability. If I say the probability that X is less than or equal, it'll be a little bit more because we can see from this graph, it's getting smaller and smaller over here. But if I say greater than 3, look how big that is. That's a very large number. Based on a Harris poll, 60% of adults believe in the devil. Assuming that we randomly select 5 adults, The probability that they believe in the devil is 0.6. 60 divided by 100. A, we want the probability that exactly 3 of the 5 adults believe in the devil. And our number is 0.3456. That's the answer to A. Now, B, the probability that the number of adults who believe in the devil is at least 2. At least 2 means 2, 3, 4, 5. I can say greater than or equal to 2. And I hit compute. And that's a huge number. I haven't found anywhere in StatCrunch to work these numbers out. For binomial distribution, if I want to find the mean or the standard deviation or both, we multiply n, which is the number of trials, times p, the probability of success. If I wanted to know the mean of 60% of adults that believe in the devil, that's equal to n times p. 5 times 0.6 is 3. The standard deviation is the square root of 5 times 0.6 times q is 1 minus p. 1 minus p is 0.4. Here n is 5. I'd multiply 5 times 0.6 times 0.4, and then I take the square root of that, and that would give me my standard deviation. I do have a couple of problems ready. Number 1, assume that a procedure yields a binomial distribution with n equals 5, and the probability of success is p equals 0.50. Use a binomial probability table. We're going to just use our binomial calculator to find the probability that the number of successes x equals 4. Here is my probability. Round to 3 decimal places, 1, 5, 6. Assume that random guesses are made for 7 multiple choice questions on an SAT test. 7 for n. Each with the probability of success or getting it right given by p equals 0.2. Find the indicated probability for the number of correct answers. The probability that the number of correct answers is fewer than 4. Fewer than 4 means less than 4. You could even say less than or equal to 3, whichever way you like. Hit compute, and there we have our answer. 4 decimal places, 1, 2, 3, 4. This last 6 goes to 7. This is the one that I wanted to do because it's manual. Let's do this. Assume that different groups of couples use a particular method of gender selection, and each couple gives birth to one baby. This method is designed to increase the likelihood that each baby will be a girl. But assume that the method has no effect. The probability of a girl is still 0.5. Assume that the group consists of 23 couples. Find the mean and the standard deviation for the number of girls in groups of 23 births. The mean is equal to n times p. Here n is 23, and the probability is 0.5. If I multiply that together, half of 23 is 11.5. Find the value of the standard deviation. The standard deviation is equal to the square root of n times p times q. That's equal to the square root of n is 23, p is 0.5, and q is 1 minus p. It's also 0.5. My standard deviation is equal to 2.39, round to 1 decimal place, 2.4. Use the range rule of thumb to find the values separating results that are significantly low or significantly high. Here in the middle, we have the mean, which is 11.5. And then from here to here is not significant. This is mu plus 2 times sigma. And this is mu minus 2 times sigma. Anything less than this is significantly low. Anything greater than that is significantly high. And anything in the middle is not significant. Now we have to figure out what those values are. We have 11.5 plus 2 times 2.4. And here we have 11.5 minus 2 times 2.4. This is 16.3. And this is 6.7. Use the range rule of thumb to find the values separating results that are significantly low or significantly high. Values of blank girls or fewer are significantly low. 6.7 on the low end. Values of 16.3 or greater are significantly high. Is the result of 21 girls a result that is significantly high? 21 girls is definitely greater than my cut point, which was 16.3. The result is significantly high because 21 girls is greater than 16.3. A result of 21 girls would suggest that the method is effective because without the treatment, we have a 50% chance of a girl and a 50% chance of a boy. But with this treatment, we're getting significantly higher values. So the treatment is effective. Thank you for watching. Have a good one. Bye.